A star does not simply go out, it fights gravity for millions, sometimes billions, of years, turning hydrogen into helium, helium into carbon, and, in the greatest stars, building layer after layer until iron gathers in the core like a final locked door. Then the ending depends on wait, a quiet white dwarf, a galaxy-bright supernova, a city-sized neutron star, or a black hole where even light cannot return. This is not only the story of stellar death, it is the story of how the universe makes the ingredients for planets, oceans, moons, and life itself. If this kind of calm space science helps make the night feel deeper, a like, a subscription, or sharing the video with someone who loves the cosmos would mean a lot. Thank you for spending your time here. What time is it where you're watching or listening, and from what place in the world, leave it in the comments. And now, let the life and death of stars begin. A star begins in darkness long before it becomes a point of light. It gathers from a cold cloud of gas and dust spread across interstellar space, where the material is thin by earthly standards but immense in reach. Most of that ancient material is hydrogen, with helium beside it, the two simplest elements left in great abundance from the earliest history of the universe. For a long time, the cloud seems almost still, yet gravity is patient. Every atom pulls on every other atom, and over vast spans of time, slight knots in the cloud draw in more matter. The more they gather, the stronger their inward pull becomes. The cloud folds toward its denser regions until a hidden center begins to form. This center is not yet a star. It is a growing seed of pressure, wrapped in gas, bright only in the future. As matter falls inward, it releases energy. The interior warms. The density climbs. What had been a loose and drifting cloud becomes a contracting sphere, and inside that sphere, the conditions move toward a threshold that ordinary matter cannot cross quietly. The atoms are no longer free to remain distant from one another. They are pressed into a hot, crowded state, stripped into plasma, a sea of nuclei and electrons. Still, gravity continues to press inward, seeking a smaller and tighter shape. The future of the object depends on whether the core can become hot and dense enough for nuclear fusion to begin. Fusion is the quiet furnace at the heart of every true star. It begins when light atomic nuclei collide with enough force to overcome their natural electric repulsion. Once they come close enough, the strong nuclear force binds them together, and a small amount of mass is transformed into energy. The change is tiny in each reaction, but the number of reactions inside a star is enormous beyond ordinary scale. In the core, hydrogen nuclei combine through a chain of reactions that ultimately builds helium. Energy moves outward from this hidden region, first through the dense interior, then toward the surface, and finally into space as light and heat. The star is born when this outward energy becomes strong enough to resist further gravitational collapse. From outside, it may appear serene, a steady point shining against the black. Inside, it is a balance held at every moment, gravity pressing inward and fusion pushing outward. This balance is called hydrostatic equilibrium, a simple phrase for a deep and delicate arrangement. If gravity grows too strong, the core tightens and heats, which increases fusion and produces more outward pressure. If outward pressure becomes too strong, the star expands slightly, the core cools, and fusion eases. In this way, the star regulates itself, not with intention, but through the rules of matter and energy. It is stable because each disturbance tends to awaken its opposite. Yet beneath all that activity, the central story remains one of balance. A star shines because it is neither winning nor losing its struggle with gravity. It is held at the boundary between collapse and dispersal. The long middle life of a star is called the main sequence, and it is the calmest stretch in the stellar story. During this time, hydrogen fusion in the core provides the energy that supports the star. For a star like the Sun, this stage lasts for billions of years. For smaller red stars, it may last far longer, because they burn their fuel slowly and carefully. For larger blue stars, it may be much shorter, because their hotter cores race through fuel at a tremendous rate. Yet whatever the size, the same basic principle remains. The apparent stillness of a star is therefore not emptiness or rest. It is motion so constant that it becomes stability. Light that leaves the surface has begun in the core as energy from fusion, then wandered outward through dense layers, absorbed and re-emitted many times before it escapes. By the time that light crosses open space, it carries a message from deep inside the star. The furnace still burns, the pressure still holds, gravity has not yet won. A star is also a maker of change. In its youth, it may be composed mostly of hydrogen and helium, but fusion begins to alter that inventory. Hydrogen becomes helium in the core, and helium slowly gathers like ash from an invisible fire. As the ages pass, the core composition shifts. The star may look almost unchanged from outside, but inside, the central supply of hydrogen is being steadily reduced. This is the hidden clock of stellar life. It does not tick in seconds. It advances through fusion, one nuclear reaction after another, until the original balance becomes harder to maintain. The quiet furnace is therefore both the source of the star's life and the measure of its eventual end. Every moment of shining spends the fuel that makes shining possible. This gives stars their strange double nature. They seem permanent because their lives are so long, and they are temporary because the process that sustains them cannot continue forever. But in the deeper time of the universe, stars are evolving bodies. They are born, they settle into balance, they age, and they move toward endings shaped by their mass. Some will fade toward white dwarfs, some will tear themselves apart in supernovae, some will leave neutron stars, where matter is crushed into a form almost beyond familiar comparison. Some will become black holes, regions where gravity curves space-time so deeply that light cannot escape. All of those endings begin with the same first question in the core. How much matter has gravity gathered? And how fiercely must fusion burn to hold it up? The answer determines the pace of the furnace. A low-mass star burns gently. Its gravity is weaker, so its core need not reach the extreme conditions of a massive star. It glows more dimly, but it may preserve its fuel for immense spans of time. A star like the Sun burns with a middle patience, bright enough to warm worlds, modest enough to live for billions of years. A massive star burns with a brilliance that looks powerful, but that power carries a cost. Its core is hotter, its reactions faster, and its life shorter. The star shines more intensely because gravity demands a stronger answer from fusion. In that demand, its future is already being written. This is why a star is not merely a ball of burning gas in the ordinary sense. Ordinary fire needs oxygen and chemical reactions. A star is powered by nuclear change, by the binding of nuclei in conditions of heat and pressure that no flame can approach. Its light is not combustion, but conversion, matter giving up a fraction of itself to become radiant energy. That conversion allows the star to remain open against gravity's inward desire. For most of the star's life, the balance seems almost timeless. Yet the balance contains a quiet asymmetry. Gravity does not need fuel. It is always present wherever mass exists. Fusion, however, depends on the supply of suitable nuclei and the conditions that allow them to meet. As hydrogen is consumed in the core, the star gradually approaches a new state. The outward pressure does not vanish at once. The furnace does not stop like a lamp switched off. Instead, the core begins to change. It becomes richer in helium. The hydrogen available in the very centre becomes scarce. The old balance begins to loosen. Gravity presses inward with the same ancient patience, and the core responds by contracting. Contraction raises temperature. Higher temperature alters the rate of fusion in nearby regions. The star, which once held itself in a long, steady rhythm, begins to move toward a different phase. The end is still far away, but the direction has shifted. The quiet furnace has made the star luminous, stable, and enduring. It has also prepared the conditions for transformation. Every white dwarf, every supernova, every neutron star, and every stellar black hole has its origin in this first balance between pressure and collapse. Stellar death is not a sudden interruption of stellar life. It is the completion of a process that begins when gravity first gathers a cloud and fusion first answers from the core. For as long as the answer is strong enough, the star shines. When the answer changes, the story of death begins, not as an ending alone, but as a deeper rearrangement of matter, energy, and time. A star's fate is written in its mass, long before its colour changes, long before its outer layers swell, and long before any final remnant is left behind. The beginning may look similar across many stellar lives, with gas collecting from a cold cloud and gravity pulling the material inward. Yet the amount of material that gathers changes everything that follows. Mass is not only a measure of size, it is the source of gravity, the builder of pressure, the keeper of fuel, and the force that decides how hot the core must become. A small star and a massive star are not simply different versions of the same flame. They live under different demands. The smaller one carries less weight above its core, so it does not need to burn as fiercely to hold itself open against collapse. The larger one carries a deeper burden of gravity, so its core must become hotter and more active, releasing far more energy just to remain stable. From this simple difference comes the great branching path of stellar evolution. The universe fills with stars of many kinds, but each one begins with a question of gathered matter. If too little mass collects, the object never becomes a true star at all. It may glow faintly from heat left over from formation, but it cannot sustain the central fusion of hydrogen that defines a star's long life. If enough mass gathers, the core reaches the necessary pressure and temperature, and hydrogen fusion begins. At that moment, the object joins the main sequence, the long band of stable stars arranged by temperature and brightness. Yet even on this steady band, mass quietly separates one destiny from another. The lowest mass stars are dim red objects. They are cool at the surface, modest in brightness, and extraordinarily long-lived. They spend their hydrogen slowly, conserving their fuel with a patience beyond measure. A star somewhat like the sun burns more brightly and moves through its life at a middle pace, steady across billions of years but not eternal. A high-mass star shines blue-white and brilliant, but its brilliance is costly. It must produce such intense outward pressure that its fuel disappears quickly. The result seems paradoxical. The stars with the most fuel live the shortest lives because their greater mass forces them to burn that fuel at an extreme rate. In the quiet arithmetic of the cosmos, abundance does not always mean endurance. It can mean urgency. This is one of the central truths of stellar death. A star does not die when it simply runs out of material. It dies when it can no longer use the right material in the right place to resist gravity. The fuel may still exist in outer layers, and heavier nuclei may remain in the core, but if the necessary fusion cannot continue where pressure is needed, the balance begins to fail. Mass determines how far the star can push this struggle. In a low-mass star, the core eventually becomes rich in helium after long hydrogen burning. It contracts and heats, and in stars with enough mass, helium can ignite, forming carbon and oxygen. But the story slows there. The core does not become hot enough to fuse carbon efficiently. Gravity presses, yet not with the overwhelming strength found in larger stars. The star sheds its outer layers and leaves a white dwarf, a dense ember no longer supported by active fusion. In a high-mass star, the greater gravitational weight drives the core to higher and higher temperatures. After hydrogen, helium burns. After helium, carbon can burn. Later still, oxygen, neon, and silicon take their turns in the inner furnace. Each new fuel requires harsher conditions than the one before it. Each stage is shorter than the last. The massive star becomes a structure of nested shells, each layer burning a different kind of fuel. While the center advances toward iron, mass gives the star permission to climb this ladder, but the climb ends at a wall. Iron is too tightly bound to provide useful energy through ordinary fusion. Once an iron core grows beyond support, gravity has no further answer from the furnace, and collapse follows. This is why mass decides not only the length of a star's life, but the manner of its death. A lighter star can end quietly, casting off a glowing shell and leaving a white dwarf behind. A heavier star can tear itself open in a supernova, scattering newly made elements across space. The remnant then depends on how much core remains after the explosion. If the collapsed core is held by neutron pressure, the result is a neutron star, a compact object where matter is crushed into a form unlike ordinary atoms. If even that pressure fails, the collapse continues into a black hole, where gravity encloses a region from which light itself cannot escape. These endings appear very different, but they are all consequences of the same original measure. Mass is destiny because it sets the pressure in the core, the pace of fusion, the sequence of fuels, and the final strength of gravity when the fuel no longer answers. The relation is not always perfectly simple, because stars can lose mass through winds, exchange mass with companion stars, or explode in ways that strip away much of their outer material. Many stars live in pairs, and one star may feed another, changing a fate that would have been different in isolation. Massive stars may blow away huge amounts of gas before their cores collapse. Rotation and chemical composition also shape the details. Yet beneath these complications, mass remains the first and deepest guide. It sets the main pressure of the story. Other factors may bend the path, but mass lays the ground beneath it. The reason is rooted in gravity's steady character. Gravity does not weaken because the star has lived for a long time. It does not become tired. And it does not depend on a fuel reserve. It simply follows mass. The more mass a star has, the more strongly it pulls itself inward. Fusion must then rise to meet that pull. In smaller stars, the contest is gentle enough that the star can burn slowly and persist. In larger stars, the contest is fierce from the beginning, and the star must answer with intensity. The brilliant blue light of a massive star is therefore not a sign of safety. It is a sign of pressure, heat, and rapid consumption. Such stars may illuminate their surroundings, carve cavities in nearby gas, and shape future star formation with radiation and stellar winds. Yet their own lives are brief by cosmic standards. They pass through the universe like bright sparks, transforming simple nuclei into heavier ones and ending with events that can alter entire regions of space. Lower mass stars are less dramatic, but they are no less important. Their long lives make them stable anchors in galaxies, and their quiet endings return enriched material to the interstellar medium through winds and glowing nebulae. A star like the Sun does not need to explode to matter to the chemical history of the cosmos. It can still build carbon and oxygen in its later phases. shed those products into space, and leave behind a white dwarf that cools through deep time. Massive stars produce many of the heavier elements and spread them with force. Lower mass stars contribute more gently and live long enough to mark the slow rhythm of galactic aging. Together, they make the universe chemically richer than the one into which the first stars were born. In the earliest times, almost everything is hydrogen and helium. Stars change that simplicity. Their mass determines how deeply they can rearrange matter, and their deaths determine how widely that rearranged matter is shared. This gives stellar mass a quiet weight in the story of the universe, not because nature chooses, but because consequences unfold from initial conditions. A star is born from a cloud, but it does not step into a blank future. Its mass carries a map of possible endings. The map may be altered by companions or winds, yet its main roads remain clear. Small stars linger. Sun-like stars swell and fade into white dwarfs. Massive stars rush toward collapse. Supernovae, neutron stars, and black holes. The night sky hides these destinies behind points of light that seem equally still, but each point contains its own clock. Some clocks move slowly, with fuel measured across spans longer than the present age of the universe. Others race in bright silence, using their abundance so quickly that their deaths seed the space around them while quieter stars are still young. In this way, mass becomes the first language of stellar mortality. It tells how strongly gravity speaks, how fiercely fusion replies, and how the reply will eventually fail. A star's death is not random. It is the final expression of the weight it has carried since birth. The first sign of a star's old age is not an explosion, but a slow inward tightening hidden beneath an outward bloom. For most of its main sequence life, the star appears steady because hydrogen fusion in the core supplies the pressure that gravity requires. The surface may shine with nearly constant brightness across spans that overwhelm any human sense of change. Yet deep inside, the fuel that matters most is being transformed. Hydrogen in the central furnace becomes helium, and helium settles into the core like a growing reserve of ash. The word ash is only an image, because this material is not cold or lifeless. It is hot, dense, and caught in the press of gravity. But it no longer provides the same easy source of energy that hydrogen once did. As the central hydrogen supply declines, the core loses part of the pressure that helped it resist collapse. Gravity responds, not as a sudden strike at first, but as a tightening grip. The core contracts, its temperature rises. Its density increases around it. Hydrogen remains in a surrounding shell, and as the contracting core heats this shell, hydrogen fusion begins to burn there more intensely. The star has not gone dark. It has moved its main burning outward, from the center into a shell wrapped around the helium-rich core. This change alters the structure of the whole star. The hotter shell releases more energy than before. The outer envelope expands. As it spreads outward, the surface cools, because the same flow of energy is now distributed across a much larger area. A cooler surface glows redder, and the star begins to leave the steady main sequence behind. It becomes a giant, not because the core has relaxed, but because the interior has become more compressed. The star grows outward while its center falls inward. This contrast gives the red giant phase its quiet strangeness. From a distance, the star seems to swell, soften, and redden, as though it is loosening into space inside. The opposite is happening. The core is becoming smaller, hotter, and more crowded. Gravity is drawing the central region down toward harsher conditions, while energy from shell burning lifts the outer layers away. The star becomes a vast envelope surrounding a compact hidden furnace. Its surface can reach far beyond its former size, and for a star like the Sun, This future expansion will one day transform the inner architecture of its planetary system. Its light will grow more luminous even as its surface becomes cooler. The red colour is therefore not a sign of weakness alone. It is the colour of an expanded surface, stretched outward by the changing physics beneath it. In lower mass stars that have enough core mass to continue, the contraction eventually drives the helium-rich centre to temperatures high enough for helium fusion. Helium nuclei are heavier than hydrogen nuclei and carry stronger electric repulsion, so they require more extreme conditions before they can fuse. When the core reaches that threshold, helium begins to form carbon through the triple alpha process, in which 3 helium nuclei ultimately combine to make a carbon nucleus. Some carbon can then capture helium and become oxygen. The star that once turned hydrogen into helium now begins to build elements more familiar to rocky worlds and living chemistry. Yet even this renewal is temporary. The star has found a new source of support, but the supply is limited, and the structure remains unstable compared with the long calm of the main sequence. In stars similar to the Sun, the onset of helium burning can occur after a dramatic internal adjustment, often called helium flash. The event is hidden beneath the surface because the outer layers do not burst apart in response. It is not a visible explosion in space. It is a rapid release of energy inside a compressed core, where helium fusion begins under unusual conditions. Afterward, the star settles into a different balance for a time. It becomes smaller and steadier than at the peak of its first red giant expansion, while helium burns in the core and hydrogen continues to burn in a shell around it. This middle calm is only another interval in a longer decline. The star has escaped one crisis by lighting a new furnace, but the same rule still governs its future. Every fuel that supports the star is gradually spent. Every successful answer to gravity prepares the next question. When helium in the core is mostly converted into carbon and oxygen, the centre again loses its main source of energy. It contracts once more. Around it, layers of burning remain helium fusion in a shell close to the core, and hydrogen fusion in a shell above that. The star swells again, entering a later giant phase that is broader, cooler at the surface, and increasingly restless. Its outer layers become only loosely held by gravity. Pulsations move through the star. The envelope expands and contracts in slow cycles, and each movement helps lift material away from the surface. Stellar winds grow stronger, carrying gas and dust outward into space. The star is now losing itself gradually. Its future white dwarf core is being uncovered from within, though it still lies buried under luminous, unstable layers. This is not death as a single moment, it is a long unbinding. The outer atmosphere drifts away piece by piece, enriched by the products of earlier fusion and internal mixing. Carbon and oxygen made in the star's interior can be carried into regions from which they may eventually escape. Dust grains can form in the cooling winds, tiny solid traces of stellar chemistry moving into interstellar space. The red giant and later giant stages therefore do more than mark a star's decline. They help return material to the galaxy. The star loosens its grip on matter that once belonged to its body, and that matter may later become part of new clouds, new stars, and new planets. The scale of the expansion can be immense, but the underlying story remains exact. Gravity compresses the core, shell fusion intensifies, the envelope responds by swelling, surface temperature falls, the colour shifts toward red. The star becomes luminous because it is so large, not because its surface is hotter. This makes red giants visible across great distances, quiet beacons of aging stellar interiors. Their glow reveals not a simple fire, but a layered structure with a dense central region, active burning shells, and a vast atmosphere that can barely remain attached. In such stars, the boundary between star and space becomes less sharply held. Gas flows outward. The surrounding environment is seeded with material. The body of the star begins to merge with the medium from which future stars may form. Massive stars also pass through giant phases, though their paths are faster and more complex. Their cores reach temperatures that allow heavier fuels to ignite, and their outer layers may swell into red supergiants or shift through other bright states shaped by winds, mass loss, rotation, and internal mixing. In them, expansion is not the final quiet loosening that leads to a white dwarf. It is one stage on the way toward deeper core burning and possible collapse. Still, the same visual paradox appears. A massive star may become enormous and red at the surface, while its center is racing toward denser and hotter states. The more peaceful color hides an increasingly urgent interior. For both modest and massive stars, the red giant transformation is a sign that the main sequence balance has ended. The star is no longer living from the simple central burning of hydrogen. Its structure has become layered, reactive, and temporary. The old stability has given way to negotiation, with each new fuel and each new shell offering only partial support. The star is still beautiful, still radiant, and still governed by balance. But the balance is now shifting rather than settled. The core keeps contracting. The envelope keeps responding. The path toward the remnant has begun. In the red giant phase, stellar death first becomes visible. It does not yet appear as a corpse, an explosion, or a vanished light. It appears as expansion, redness, and brightness spread over a fragile outer atmosphere. The star grows larger because its center is running out of ways to resist gravity. It becomes more luminous because its inner crisis sends energy through a swelling envelope. It sheds material because its outer layers are no longer tightly bound. Quietly, over ages, the star begins to separate into what will be lost and what will remain. The lost material drifts outward. The remaining core contracts toward a future of extraordinary density. The red giant is therefore a passage between the long life of fusion and the strange afterlife of remnants. It is the moment when the star's hidden aging becomes a visible shape, and the universe shows that even expansion can be a form of collapse. A lower mass star does not end by tearing itself apart. Its death is quieter and slower, because the star fades into a remnant that is both small and extraordinarily dense. After the red giant phase, the star has already changed beyond its long main sequence form. The old hydrogen burning core is gone. Helium has been fused into carbon and oxygen if the star is massive enough for that stage. But the central region cannot keep climbing into heavier fuels. The conditions are not extreme enough to ignite carbon fusion. Gravity keeps pressing inward, yet the star lacks the mass needed to drive the core to the next threshold. The outer layers, swollen and loosely held, drift away under pulsations and stellar winds. The bright envelope that once made the star appear enormous is gradually lifted from the compact center. What remains is the bare core, no longer wrapped in the same deep atmosphere, no longer powered by active fusion. It is hot because it has been compressed and heated through the star's final phases. It shines because it still contains stored thermal energy, but it is no longer a living furnace in the old sense. It is a white dwarf, the quiet remnant of a star that was not massive enough to die in a supernova. The phrase can seem gentle, but the object itself is one of the densest forms of matter found outside collapsed stellar cores. A white dwarf may contain a star's former core mass packed into a sphere roughly comparable in size to Earth. Its surface can be intensely hot at first, glowing white or blue-white, but its size is so small that its total light is modest compared with the star it once was. The red giant had spread itself across a vast volume. The white dwarf gathers the remaining core into compact silence. It is a star reduced to an ember, but the ember is made of matter under pressure far beyond ordinary experience. The reason it does not collapse further is not that fusion still pushes back. Fusion has mostly ended. Instead, support comes from a quantum property of electrons. In ordinary matter, electrons occupy states around atomic nuclei, and the spaces between atoms are large compared with the nuclei themselves. In a white dwarf, matter has been compressed so strongly that the atoms lose their familiar separateness. The nuclei are packed in a dense sea of electrons. These electrons resist being squeezed into the same states. This resistance is called electron degeneracy pressure. It is not heat pressure in the usual sense, and it does not depend on the white dwarf staying hot. It arises from the rules that govern particles at the smallest scales. Gravity presses inward. Electron degeneracy pressure answers, holding the object up even after the fusion furnace has gone still. This makes the white dwarf a different kind of stellar body from the star that created it. A main sequence star remains stable because heat from fusion supports it. A red giant swells because shell burning and core contraction reshape its balance. A white dwarf is supported by the behavior of matter itself under extreme compression. It is not actively producing the energy that holds it against gravity. It is being held by the refusal of electrons to be crowded without limit. The remnant becomes a boundary object, still star-like in appearance, but no longer alive by stellar fusion. It can shine for immense lengths of time as it cools, but that light is the slow leakage of stored energy. There is no new central fuel source waiting to be ignited in an ordinary white dwarf. No fresh layer begins to burn and restore its old size. Its future is cooling, fading, and settling deeper into darkness. The maximum mass for this kind of support is known as the Chandrasekhar limit, about 1.4 times the mass of the Sun. Below this limit, electron degeneracy pressure can hold the white dwarf against collapse. Above it, the support fails. This boundary is one reason stellar mass matters so deeply. The remnants of lower mass stars can become white dwarfs because their remaining cores fall below that limit. If a white dwarf gains too much mass from a companion star, or if a stellar core is born too heavy in the first place, the story changes. Collapse or explosion can follow. In the quiet path of a single sun-like star, however, the core remains light enough to settle into white dwarfhood rather than plunge further inward. The density of such a remnant is difficult to hold in ordinary thought. A small spoonful of white dwarf material would weigh tons on Earth, because familiar nuclei and electrons are packed into an unfamiliar state. Carbon and oxygen, elements associated with soot, stone, air, and life, can be compressed into a body with the mass of a star and the size of a planet. The white dwarf therefore joins two scales that rarely meet in daily imagination. It has the dimensions of a world, but the gravity of a stellar corpse. Its surface gravity is enormous. Its atmosphere, if present, is thin and pressed close. Everything about it speaks of compression, of a once vast star drawn inward until only the resistant core remains. Yet the formation of a white dwarf is not isolated from the space around it. The remnant is usually surrounded at first by the material the star has shed. Ultraviolet radiation from the hot exposed core streams into that expanding gas and makes it glow. For a time, the dying star becomes both a tiny intense center and a delicate luminous shell. The shell will become a planetary nebula, though the name is misleading. It has nothing to do with planets except for an old resemblance seen through early telescopes. The nebula is the star's own outer atmosphere, released and lit from within. At its center, the white dwarf remains. Marking the place where the core survived after the envelope escaped, over time, The nebula expands, thins, and blends into the interstellar medium. The white dwarf stays behind, cooling at the center of a fading memory. Cooling is the long final chapter. A young white dwarf can be extremely hot, but without fusion it can only radiate away what energy it has. As it cools, its color shifts. White gives way to yellower and redder tones, then to dimmer states that are harder to detect. In theory, after an immense span far longer than the current age of the universe, a white dwarf may cool into a black dwarf, a cold dark remnant no longer giving off significant light. But the universe is not yet old enough for true black dwarfs to exist. Every white dwarf known still carries some heat from its past. Their cooling helps astronomers estimate the ages of old star clusters. The white dwarf ending is peaceful only when compared with the violence of supernovae. It is still the result of a profound transformation. A star loses its outer layers, exposes its core, and leaves behind matter in a state that cannot be produced in ordinary planetary environments. Its stability is austere. It is a balance without flame, pressure without burning, light without renewal. Its surface glows above an interior where carbon and oxygen nuclei sit in a dense arrangement, surrounded by electrons that support the whole body. The former star has become a compact archive of its own life, preserving the ashes of helium burning in a form that may persist for trillions of years. Around it, the expelled gas carries other parts of the story away. Some of that material may eventually mix into a molecular cloud. It may join the raw ingredients of another generation of stars. It may become part of dust grains, comets, planets, or atmospheres. The white dwarf itself may remain alone, slowly dimming. Even the quiet remnant can have a complicated afterlife if another star remains nearby. But in the basic path of a solitary lower mass star, the white dwarf is the final compact answer to gravity. It does not explode. It does not collapse into a neutron star. It does not become a black hole. It simply endures, dense and cooling, while the material it released drifts outward into the galaxy. In this ending, stellar death becomes almost silent. The star that once filled space with a vast red envelope leaves a point-like remnant smaller than many planets. Its active fire is gone, yet its existence reveals the deep rules beneath ordinary matter. Gravity has pressed inward until electrons themselves become the support. The white dwarf shines with leftover heat, not as a promise of renewed fusion, but as a slow farewell from the core. It is the small silent remnant that remains when a star has spent its central fuel, shed its outer body, and settled into the long dark patience of cooling time. The outer layers of a dying lower mass star do not vanish when they leave the star. They spread outward as a glowing remnant of atmosphere, thin and delicate, yet rich with the history of the furnace that once burned beneath them. This is the planetary nebula stage, a name born from old telescopic confusion rather than from any true connection to planets. Through early instruments, some of these round, faint clouds looked like distant planetary disks, soft and pale against the dark. The name remained, even after the nature of the objects became clearer. A planetary nebula is not a world, and not the birthplace of a world by itself. It is the released envelope of a star that has passed through its red giant and asymptotic giant phases, a luminous shell of gas expanding away from a hot exposed core. At the centre sits the young white dwarf, small, dense, and intensely hot. Around it drifts the material that once made the star wide and red. The scene is quiet compared with a supernova, but it is not empty. It is one of the ways a star gives part of itself back to the galaxy. The glow begins because the bare core is hot enough to pour high-energy ultraviolet light into the surrounding gas. That radiation strips electrons from atoms in the expanding shell. When electrons later fall back or shift into lower energy states, the gas emits light. Different elements shine in different ways, and the nebula can reveal hydrogen, helium, oxygen, nitrogen, carbon, and other traces of the star's inner work and surface mixing. The gas is responding to radiation from the central remnant, turning an otherwise fading death into a brief lantern in interstellar space. Brief, in this context, still means thousands or tens of thousands of years. Against the lifetime of the star, it is only a last exhalation. Against human time, it is ancient and slow. The expanding shell does not form all at once as a perfect bubble. It is shaped by winds, pulses, magnetic fields, rotation, and sometimes by the pull of a companion star. During the late giant phases, the star loses mass through strong stellar winds. These winds may change speed over time. A slower earlier wind can be overtaken by a faster later wind from the exposed central core. When the faster material catches the slower material, it compresses and shapes the gas into shells, rims, knots, filaments, and lobes. Some nebulae appear nearly round. Some stretch into hourglass forms. Some show rings, jets, or layered halos like old breaths preserved one inside another. Their beauty is therefore not decoration placed on a simple event. It is the visible trace of complicated mass loss, changing radiation, and the geometry of a dying stellar system. The nebula records how the star lets go. Inside that released gas lies a modest but important share of cosmic chemistry. A star like the Sun spends most of its life turning hydrogen into helium, but in its later stages it can fuse helium into carbon and oxygen. Convection and internal mixing can bring some newly formed material toward the outer layers. As winds lift those layers into space, the products become part of the interstellar medium. The star does not create the heaviest elements in large amounts. It does not make gold or uranium through the ordinary path of a planetary nebula. Those require more violent or exotic settings, such as supernovae and neutron star mergers. But quieter stars contribute meaningfully to carbon, nitrogen, oxygen, and dust that enrich galaxies across time. Their deaths are not only dim endings, they are slow acts of return. The released material moves outward into a medium already shaped by many generations of stars. Some regions of space are thin and hot. Others are cold and dense enough to become molecular clouds. The nebular gas will eventually thin until its boundaries blur. Its atoms will mix with the surrounding material, losing the clear form that made the nebula visible. The white dwarf will continue cooling. The shell will fade, yet the atoms do not disappear. They remain in the galaxy, available for later gathering. Gravity may one day draw a small portion of this enriched gas into another cloud. Within that cloud, dust helps shield molecules from harsh radiation and allows cooling. Cooling helps gas contract. Contraction may lead to new stars, and around some of those stars, disks of leftover material may form planets, moons, asteroids, and comets. In that long chain, the planetary nebula becomes one quiet passage between old stars and future worlds. The link should not be made too simply. A single nebula does not instantly become a new solar system, and most of its gas will drift, mix, and scatter before any part of it joins a new birth cloud. But the principle is profound. The matter in rocky planets and living chemistry requires elements beyond hydrogen and helium. Stars manufacture many of those elements, and dying stars release them. A planetary nebula shows that release in a visible, graceful form. It is stellar memory becoming galactic supply, the carbon in drifting dust, the oxygen in glowing gas, and the nitrogen carried outward are no longer locked inside the star that made or processed them. they have entered the larger circulation of the galaxy. This circulation is slow, uneven, and vast, a gradual enrichment rather than a perfect repeating cycle. The first stars formed from simpler material. Later stars formed from gas already touched by earlier stars. Planetary nebulae are part of that enrichment, especially for elements and dust returned by low and intermediate mass stars. Their contribution is less violent than the blast of a massive star, but because such stars are numerous, their accumulated effect is wide. The galaxy becomes chemically layered through many kinds of death. Some deaths explode, some shed, some collapse into darkness. Some leave glowing shells that fade into invisibility while their material continues on. At the heart of the nebula, the white dwarf plays the role of both remnant and lamp. Its ultraviolet light gives the surrounding gas its temporary radiance. Yet the white dwarf is also withdrawing from the story. It has no strong wind forever, no endless supply of heat. As it cools, its ability to ionize the nebula weakens. Meanwhile, the gas expands and becomes more diffuse. The light fades from both sides, the lamp cools, and the lantern thins. In time, the nebula becomes too faint to see. The once vivid structure dissolves into the background of interstellar matter. The transition is gentle, not sudden. A planetary nebula is therefore an object defined by impermanence. It is visible only during a narrow window, after the star exposes its hot core and before the shell spreads too far. This fleeting visibility gives planetary nebulae their haunting quality. They are not the long life of a star and not the nearly eternal cooling of a white dwarf. They are the luminous interval between the two, the moment when the lost atmosphere still holds a shape and the exposed core still has enough heat to make it shine. In that interval, astronomers can study the final mass loss of Sun-like stars, the chemistry of the expelled gas, and the conditions that lead from red giant to compact remnant. Some planetary nebulae reveal round symmetry, others reveal deep asymmetry, suggesting that solitary stars may not explain every form. Companion stars can disturb the outflow, drawing gas into disks, shaping jets, or helping carve bipolar lobes. Even planets, if they survive close enough and interact with the expanded envelope, may influence details, though stronger shaping often comes from stellar companions. The dying star is not always alone, and its final atmosphere may carry signs of those relationships. In this way, a planetary nebula can preserve not only nuclear history, but orbital history, the hidden architecture of a system exposed at the end of stellar life. Still, the larger meaning remains calm. The star has not been wasted. Its outer layers become a fading cloud. Its core becomes a white dwarf. Its atoms separate into new futures. The nebula's glow is a farewell, but it is also a release from confinement. Matter that spent billions of years bound inside one star moves back into open space. The boundary between star and galaxy softens. The body of the star becomes environment. The environment becomes reservoir, far ahead, under conditions not yet arranged. Some of that reservoir may help build another star, another disk, another cold grain of dust, another rocky surface. The planetary nebula afterglow is therefore not merely the decoration around a dead star. It is a visible sign that stellar death can be generous. It shows the universe working without hurry, taking the products of a long quiet furnace and letting them drift outward, where gravity, cooling, and time may someday gather them again. A massive star begins with the same ingredient as a smaller star, a cloud that gravity persuades to fall inward. At first, the difference is only amount. More gas gathers, more dust is caught in the collapse. The forming centre gains weight, and with that weight comes a deeper pull. This larger newborn star is not simply a brighter version of a modest one. Its entire interior is forced into a more extreme conversation with gravity. The core must become hotter, denser, and more active in order to keep the star from collapsing under its own mass. When hydrogen fusion begins, the star joins the main sequence, but it arrives there already carrying a harsher fate. Its light is often blue or blue-white, its surface hot, its radiation intense, its winds strong enough to push on the surrounding gas from which it formed. In a nursery of stars, the most massive members can dominate the region. They flood nearby space with ultraviolet light. They carve bubbles into the cloud. They heat and ionize gas, stripping electrons from atoms and making nebulae glow. Around them, new star formation may be disrupted in some places and compressed into motion in others. Yet while they reshape their surroundings with brilliance, they are spending their own lives quickly. Their brightness is not a sign of long endurance. It is the visible cost of supporting great mass against gravity. The more massive the star, the stronger the inward pull, and the stronger the fusion furnace must become to answer it. In smaller stars, hydrogen fusion can proceed at a measured pace, with the core producing just enough pressure to remain balanced across billions of years. In massive stars, the pressure requirement is far greater. The core temperature rises to conditions where fusion reactions happen much faster. The star may contain much more hydrogen than the Sun, but it uses that fuel at such an enormous rate that its life is shortened. This is the great reversal of stellar abundance. More fuel does not guarantee more time, because the engine is forced to run hotter. The most luminous stars live as though their futures have been compressed. Their main sequence lifetimes may last only millions of years, a brief interval beside the slow history of smaller stars. A red dwarf can linger for spans far beyond the current age of the universe, while a massive blue star may be born, shine, evolve, and die before a quiet solar-type star has noticeably changed. This rapid life is not careless or chaotic, it is direct response to physics. The core is buried under so much material that gravity demands a powerful outward pressure. Fusion provides that pressure, but in doing so it consumes the central hydrogen at a furious pace. Massive stars also differ in the way energy moves through them. Their interiors are shaped by steep temperature differences, strong radiation fields, and regions of convection, where hot material rises and cooler material sinks. Mixing can carry fresh hydrogen into the core and move fusion products outward, altering the star's later path. Radiation itself becomes a major force. Light produced in the core pushes on matter as it struggles outward, and in the most luminous stars, this radiation pressure helps drive material away from the surface. Some massive stars shed huge amounts of their outer envelopes, changing what kind of star they appear to be and what kind of explosion they may later produce. Mass is the first guide, but it is not the only sculptor. Rotation can stir the interior. A companion star can pull material away or donate material, reshaping the life of both objects. Still, even with these complications, the central theme remains. A massive star is driven by strong gravity into high-temperature fusion, and high-temperature fusion moves quickly. The star's path after core hydrogen is exhausted begins with a familiar shift. The core contracts because its main source of pressure is weakened. Surrounding hydrogen may continue burning in a shell. The outer layers respond by expanding, and the star can swell into a supergiant. Some become red supergiants, immense and cool at the surface, with envelopes spread across vast distances. Others pass through blue or yellow supergiant phases, depending on mass loss, composition, and internal structure. The surface appearance may change dramatically, but the most important action remains hidden. The core is growing hotter. It is preparing to burn fuels that smaller stars cannot reach. In a lower mass star, helium fusion may build carbon and oxygen, but the core usually stops there. In a massive star, gravity presses harder. After the central hydrogen is gone, helium can burn into carbon and oxygen. When helium is spent, the core contracts again. This contraction heats it further, and carbon can ignite. Later, as each fuel is consumed, the center tightens again, raising the temperature to the next threshold. Neon can burn. Oxygen can burn. Silicon can burn. Each new stage supports the star for a shorter time than the one before it. Hydrogen burning may last millions of years. Helium burning is shorter. Carbon burning is shorter still. The final stages can pass with astonishing speed compared with the star's earlier life. The star is not aging gently now. It is moving through a sequence of increasingly demanding fuels, each one harder to ignite and less generous in time. This does not mean the star is visibly exploding at each stage. From outside, it may remain a luminous supergiant, perhaps unstable, perhaps losing mass, perhaps varying in brightness. The core, however, is changing with urgency. It becomes layered, with different shells burning different fuels around a central region. The structure is often compared to an onion, not because it is simple, but because fuel and ash arrange themselves in nested zones. Hydrogen may burn in an outer shell, helium burns deeper in, carbon, neon, oxygen, and silicon occupy inner regions depending on the star's stage. Each layer exists because each type of fusion requires a different temperature, and only the deeper, hotter regions can sustain the heavier reactions. In the center, the products of these reactions accumulate, building toward iron group nuclei. This layered burning makes the massive star a factory of elements, though the word factory can make the process sound too orderly. The star is turbulent, pressured, radiant, and unstable. It manufactures not with design, but with compression and heat. It builds nuclei because gravity forces matter into conditions where fusion becomes possible. The brilliance of the star's surface gives little hint of the complexity beneath it. A blue main sequence giant, a red supergiant, and a stripped hot star may represent different outward faces of the same underlying struggle. The speed of this evolution also changes the star's relationship with the galaxy. Massive stars are rare compared with smaller stars, but their effects are large. Their radiation shapes nebulae. Their winds inject energy and enriched matter into surrounding clouds. Their short lives mean they die near the regions where they were born, often still close to other young stars and gas. When they finally collapse, their explosions can stir the local interstellar medium, compress nearby clouds, and scatter heavy elements into space. In this way, the massive star's brief life leaves a wide imprint. It spends its fuel quickly, but its influence reaches far beyond its own surface. The path is therefore both magnificent and doomed. The star's great mass gives it power, but that same mass prevents a long, calm life. It cannot preserve itself by burning slowly, because slow burning would not supply enough pressure. It cannot stop gravity by choice, because gravity is the shape of its own matter pulling inward. It must shine fiercely in order to exist at all. Every intense photon escaping the surface is part of the cost of balance. Every nuclear reaction in the core delays collapse while also moving the core closer to a state where the next fuel must be found. The massive star is always buying time, and the price rises as the fuels grow heavier. By the time it becomes a supergiant with a deeply layered interior, the future has narrowed. It may lose more mass, it may change color, It may reveal deeper layers if winds or a companion strip away its envelope. But the core is advancing toward a point where fusion will no longer give back usable energy. The massive star path is a road of increasing heat and decreasing time, a sequence in which brilliance conceals acceleration. From the outside, the star may look steady enough to belong to the permanent sky. Inside, the furnace is climbing through fuels faster and faster, pressed onward by the weight of all the material above it. Its death will not be the small cooling of a white dwarf. Its mass has carried it beyond that quiet ending. It is moving toward iron, toward collapse, and toward a final event that can outshine a galaxy. Inside a massive star, the final life of the furnace becomes layered, compact, and increasingly strange. From the outside, the star may be swollen into a supergiant, making its earlier main sequence body seem small. Its surface may glow red and cool, or it may appear hotter if winds have stripped away much of the outer envelope. But the surface tells only the outermost part of the story. Deep below, where pressure rises with every layer of mass above it, the core is dividing into regions of different fire. Each region contains a fuel that can burn only under the conditions available there. The cooler outer shells still hold hydrogen and helium. Deeper zones are hot enough for carbon, then neon, then oxygen, and finally silicon. The arrangement is often described as onion-like, because the star holds nested shells around a central core. Yet this is not a neat vegetable in space. It is a turbulent, unstable, radiant body, with shells that can shift, mix, pulse, and interact as the star approaches the limit of what fusion can provide. The layered structure forms because every stage of nuclear burning leaves behind ash that can become the next fuel, if the core grows hot enough. During most of the star's stable life, hydrogen fusion produces helium. When central hydrogen becomes scarce, the core contracts and heats until helium can fuse into carbon and oxygen. When helium is spent in the center, gravity presses again, temperature rises again, and carbon can ignite. Carbon burning creates heavier nuclei, including neon, sodium, and magnesium. Later contraction raises the temperature to conditions where neon burning becomes possible. Oxygen burning follows under harsher conditions, building elements such as silicon, sulfur, and phosphorus. Silicon burning then proceeds through reactions that lead toward iron group nuclei. At each step, the star is trying to answer gravity with a new source of energy. At each step, the answer lasts for less time. The earlier fuels give the star long intervals of support, but the later fuels are consumed quickly, and the core moves through them with growing urgency. This shortening happens because the reactions become more extreme, and because some energy escapes in a quiet but decisive way. In the deep core of a massive star, very high temperatures allow the production of neutrinos, tiny particles that carry energy away almost directly. Light produced inside a star may wander for a long time before reaching the surface, but neutrinos can leave far more easily. They cool the core even while the star is trying to support itself. As a result, the final burning stages cannot be leisurely. The star must burn fuel rapidly to replace energy that is being lost. The core becomes a place of creation and leakage, a furnace that grows hotter while time grows shorter. This is part of the quiet tension hidden within a massive supergiant. The star appears vast, but its deepest clock is speeding up. The onion layer core is also a map of temperature. Hydrogen burning can occur in a shell farther from the center, where conditions are still mild compared with the central furnace. Helium burning lies deeper. Carbon burning requires more heat, and therefore sits closer to the core. Neon and oxygen occupy still more extreme zones. Silicon burning happens in the hottest inner regions, nearest the center, where the pressure is greatest. The star does not choose this order. It is imposed by the physics of nuclei. Heavier nuclei carry more positive charge, so they repel one another more strongly. To fuse them, the core must be hotter, pushing them together with greater energy until the nuclear force can bind them. This is why a smaller star stops at carbon and oxygen. Its gravity cannot make the core hot enough to continue. A massive star can go farther because it carries more weight, and that weight turns contraction into heat. Yet even massive stars cannot climb forever. The inner ladder of fusion has a final rung. The reason lies in binding energy, the measure of how tightly particles are held inside atomic nuclei. For lighter elements, fusion can release energy because the newly formed nucleus is more tightly bound than the ingredients that made it. The star gains usable energy, and that energy helps hold gravity back. This works for hydrogen becoming helium, for helium becoming carbon and oxygen, and for later stages that build toward the iron group. But iron and nearby nuclei are among the most tightly bound. Fusing iron into heavier nuclei does not release energy in the ordinary way. It requires energy. For a star that survives only by producing outward pressure, this is a dead end. Iron is not simply another fuel waiting its turn. It is the ash of the final furnace, the place where the old bargain between fusion and gravity begins to fail. As silicon burning continues near the center, iron group material accumulates. The core becomes heavier and denser, but it is no longer preparing for a stable next stage of burning. Around it, shells may still be active. Silicon may burn above the iron center, oxygen may burn farther out, neon, carbon, helium, and hydrogen may continue in their own regions, each shell adding energy and changing the layers above and below. The star has become a stack of temporary supports surrounding a center that cannot ignite into useful new life. The outward appearance may still be luminous, perhaps immense, perhaps surrounded by strong winds and lost material, but the core has crossed into a different future. It is building iron group nuclei that cannot stop collapse by fusion once the supporting conditions fail. This inner structure is delicate in a severe way. The shells are not rigid walls. They are regions of temperature and composition. Convection can churn material. Waves can move through the interior. Burning can flare unevenly. The core can grow as shell burning drops new ash inward. All of this unfolds beneath a star whose surface may give only indirect hints of the storm below. Astronomers infer the hidden structure through models, spectra, neutrinos, remnants, and the behavior of massive stars near the ends of their lives. No telescope sees the onion core directly in an ordinary living star. The layered core is a scientific reconstruction built from physics and observation, a way of understanding what must occur when mass, heat, and nuclear reactions follow their rules inward. Its importance is enormous, because this hidden structure decides what the star can give to the universe. Elements up to the iron group can be made during these burning stages. Carbon, oxygen, neon, magnesium, silicon, sulfur, calcium, and many others owe much of their cosmic abundance to stellar interiors and explosive endings. The layers of the massive star are therefore chemical reservoirs. Each shell holds products formed under different conditions. When the star later explodes, these layers may be thrown into space, though some material may fall back toward the remnant depending on the force of the explosion and the mass of the core. The future abundance of interstellar gas depends partly on how these shells are arranged before collapse. The quiet, hidden order of the onion core helps shape the visible chemistry of future generations. There is also a deeper silence in the iron center. It is not silent because nothing is happening. It is silent because the next change is not a new flame, but a loss of support. The core is hot, dense, and filled with particles moving at immense speeds. Electrons are crowded, nuclei are pressed together, radiation is trapped and intense. But the central question has changed. Earlier in the star's life, contraction brought rescue. A shrinking core heated until a new fuel ignited, and fusion restored pressure for a time. Now contraction approaches iron, and iron does not offer that rescue. The familiar pattern breaks: gravity, which has been answered again and again by hydrogen, helium, carbon, neon, oxygen, and silicon, reaches a material that cannot answer in the same language. The star is still shining, still layered, still vast, yet the center is becoming an ending. The onion layer core is therefore one of the most important hidden structures in the universe. It is where simple gas becomes a sequence of elements, where the pressure of a massive star forces matter through one burning stage after another, and where the last useful fuel gives way to iron. It shows that stellar death is prepared long before the visible explosion. The supernova is sudden to outside observers, but the groundwork is laid in the deep interior, shell by shell, ash by ash, contraction by contraction. The star carries its own future inward. Beneath the glowing envelope, its outer layers may drift in wind and light. Its inner layers narrow toward the final element. At the center, iron gathers, stable and unhelpful, the quiet sign that the furnace has nearly reached the edge of its power. Iron gathers at the center of a massive star like a final answer that gives nothing back. For most of the star's life, collapse has been delayed by a repeating pattern. Fuel in the core becomes scarce. Gravity tightens its grip. The core contracts, heats, and reaches a new threshold. A heavier fuel begins to burn, and the star finds another temporary balance. Hydrogen gives way to helium. Helium gives way to carbon and oxygen. Carbon, neon, oxygen, and silicon follow in harsher and shorter stages, each one demanding more heat, each one lasting less time. The star seems to survive by turning crisis into ignition, yet this pattern depends on one essential fact. Fusion must release energy. The new nuclei must be more tightly bound than the old ingredients, so that a small difference in mass can emerge as outward pressure, light, and heat. For a long span of stellar evolution, that bargain works. It does not work forever. When the center becomes rich in iron group nuclei, the bargain reaches its end. Iron is powerful in a different way, because its nucleus is already bound with great efficiency. To force iron into still heavier nuclei does not provide the star with useful energy. It costs energy. The furnace that has repeatedly answered gravity arrives at a substance that cannot become the next ordinary fuel. This is why iron is so important in the death of a massive star. It is not merely another element in the sequence. It is the point where fusion ceases to be rescue. Around the iron core, shells of burning can still continue for a time. Silicon may burn in a shell, adding more iron group material to the center. Oxygen, neon, carbon, helium, and hydrogen may continue in more distant layers, each shell glowing in its proper range of temperature and pressure. The star is not dark. The surface may still shine with the brightness of a supergiant. The outer envelope may still be enormous. Winds may still carry matter away. But the deep center has entered a state where the old rhythm is failing. The iron core grows, supported not by a new burning stage, but by pressure from crowded particles and the heat trapped within it. This support is temporary, as more ash falls inward from the surrounding shells. The core approaches a limit, its mass increases, its density rises. The particles inside are pressed into smaller spaces. Electrons, which once helped provide pressure against gravity, become crowded into a condition where quantum rules matter more than ordinary heat. In the iron core of a massive star, the burden is great and the situation unstable. The core is still inside a living star, still growing, still heated by surrounding burning, still losing energy through neutrinos that escape with quiet efficiency. The pressure support becomes less able to answer the inward pull. Gravity has simply waited until the furnace has no new fuel that can push back. As density climbs, another change begins. Electrons can be forced into protons inside atomic nuclei, producing neutrons and neutrinos. This removes electrons that had helped support the core. It also releases neutrinos that carry energy away. Both effects make collapse easier. At the same time, intense radiation in the core can break apart heavy nuclei into lighter pieces, a process that consumes energy rather than releasing it. The core is robbed in more than one way. Pressure weakens, energy is absorbed, neutrinos flee, matter becomes more neutron-rich. The center of the star is no longer climbing toward another stable flame. It is being prepared for a fall. The scale of the change is difficult because the outer star gives little warning in ordinary sight. A massive star can look like a luminous giant while its core is only moments away from catastrophe. The surface is far from the center, and the final changes unfold deep inside, hidden by layers of hot plasma. The star's visible light may not announce that the central support is failing, yet within the core the collapse accelerates. Once pressure can no longer balance gravity, the inward motion becomes sudden. Matter falls toward the center at a significant fraction of the speed of light. The iron core, which had seemed like the final dense heart of the star, contracts violently. Atomic nuclei are crushed. Electrons and protons merge into neutrons. The density rises toward that of an atomic nucleus, but now spread across an object the size of a city rather than a particle. This is not a gentle continuation of earlier contraction. Earlier contraction heated the core until a new fuel ignited. This contraction has no such rescue. It is a runaway. The star has crossed from adjustment into collapse. For a brief interval, gravity wins almost completely. The core falls inward until the inner region becomes so dense that nuclear forces and neutron pressure resist further compression. The infalling material stiffens against itself. The inner core rebounds, and a shock wave begins moving outward into the still falling outer core. The event is complex and not simply a clean bounce that throws the star apart by itself. Neutrinos, turbulence, rotation, magnetic fields, and the structure of the star all influence whether the shock is revived and how the explosion develops. But the essential turning point remains the same. Iron has ended the useful fusion sequence. The core has collapsed because no ordinary burning can hold it up. What follows is the attempt of the collapsing star to release the gravitational energy of that fall into an explosion. This moment reveals how deeply the star's death depends on binding energy. The star has spent its life making heavier nuclei because lighter nuclei can fuse and release energy. But iron sits near the bottom of the energy valley, where nuclei are already strongly bound. From there, fusion upward is no longer an energy source for the star. The same stability that makes iron common in stellar remnants makes it deadly to the furnace. It is ash that cannot burn usefully. It is not poisonous in a chemical sense, and it does not destroy the star by reacting badly. It destroys the balance by refusing to become fuel. Gravity demands pressure. Iron gives none through ordinary fusion. The collapse is therefore not an accident added from outside. It is the natural consequence of success. The star has fused lighter elements through stage after stage until it has built the material that marks the end of that path. In this way, the iron core is both achievement and failure. It is the product of immense heat, pressure, and nuclear history. It contains matter transformed by the star's entire massive life, yet it cannot continue the work that formed it. The core becomes a sealed question at the center of the star. How can a furnace survive when its ash is too stable to burn? It cannot. The answer is collapse. This gives the last quiet minutes of a massive star a strange dignity. The coming explosion may be violent enough to scatter elements across light years, but the cause is not chaos. It is a balance reaching its mathematical end. Pressure fades where it is needed most. Gravity gathers its long advantage. The core falls. The outer shells, still rich with the products of previous burning, are caught in the consequences. Some will be driven outward in the supernova. Some may fall back depending on the explosion. The remnant will become a neutron star or, if the remaining mass is too great, a black hole. But before any of those visible outcomes, there is this hidden crossing, the point where iron stops the fire. The image of a star as a flame can obscure the precision of what happens. A flame on Earth ends when fuel or oxygen is gone. A massive star ends because its core reaches a nuclear arrangement that cannot pay the energy debt of further fusion. It is still hot beyond ordinary comparison and full of matter in motion, yet heat alone is not enough. The star needs a pressure source that can replace what gravity removes. Iron cannot provide it. Once the core grows too massive for its available support, the fall begins, and the ancient contest between gravity and fusion changes forever. Gravity no longer waits for the next ignition. There is no next ignition that can save the iron center. The star's life has been a series of delays, each brilliant, each fruitful, each making the universe richer. Iron is the end of delay. It is the quiet threshold before brightness becomes catastrophe, before the hidden core becomes a collapsing remnant, before the outer layers are thrown into space. In that final inward motion, the star reveals the deepest rule of its life. Fusion can hold gravity back only while it gives energy away. When the giving stops, the light of the star is no longer enough to support the weight of its own heart. The supernova begins where ordinary starlight cannot reach, in the collapsing core of a massive star whose iron center has lost the power to support itself. The surface may still be spread wide as a supergiant, luminous and calm to distant eyes, but beneath its outer layers the central balance has already broken. Gravity pulls the core inward with overwhelming force. Electrons are driven into protons, making neutrons and neutrinos. Heavy nuclei are torn apart by intense radiation, stealing energy at the worst possible moment. The fall accelerates. Matter that once occupied a region larger than a planet is crushed toward a sphere only the size of a city. The inward motion is so sudden that the outer layers have no time to respond as a whole. They are still falling behind the core, still arranged in shells of hydrogen, helium, carbon, oxygen, silicon, and other products of the star's long burning. When the center reaches nuclear density and stiffens, the inner core resists compression. In that instant, the collapse changes character. The center rebounds, and a shockwave begins to move outward into material still rushing inward. This is the beginning of the visible death, though the struggle is not yet simple. The first shock loses energy as it pushes through the dense core, especially as it breaks apart heavy nuclei. For a successful core collapse supernova, the shock must be strengthened by energy carried through the star, much of it associated with neutrinos pouring out from the newborn compact remnant. These neutrinos are nearly ghost-like particles, able to pass through matter with little interaction, yet in the extreme density just above the core, enough of them deposit energy to help revive the stalled shock. Turbulence, convection, rotation, and magnetic fields may also shape the outcome. The supernova is therefore not merely the outer layers bouncing off a hard center in a simple burst. It is a deep gravitational collapse converted, imperfectly and violently, into an outward explosion. Most of the gravitational energy released escapes as neutrinos, invisible to human eyes. Only a small portion becomes the blast that tears the star open. Yet that small portion is enough to unbind much of the star and send its outer layers into space at tremendous speed. The explosion moves outward through the onion-layered body, crossing zones built over the star's whole life. It passes through silicon-rich regions, oxygen-rich layers, carbon and helium shells, and perhaps a vast hydrogen envelope if the star has kept one. As it travels, it heats and compresses matter. New nuclear reactions occur in the blast. Some elements are made in the final burning before collapse, others in the passage of the shock, and still others through environments rich in neutrons. Radioactive nuclei are also formed, and their decay can power the fading light after the initial flash. Nickel can decay into cobalt, and cobalt into iron, releasing energy that keeps the expanding debris glowing for weeks or months. The star's death becomes visible across interstellar distances because the ejecta are hot, dense enough to radiate, and expanding with enormous energy. A supernova can rival the brightness of an entire galaxy for a brief time, even though it comes from a single star. That brightness is not steady like the main sequence life that came before. It rises, peaks, and fades as the debris expands and cools. The light curve, the pattern of brightening and dimming over time, carries information about the star that died, the material it lost before death, and the radioactive products forged in the explosion. Different supernovae reveal different histories. Some massive stars still possess thick hydrogen envelopes when they collapse, and their spectra show hydrogen. Others have been stripped by winds or companion stars, leaving explosions with little or no hydrogen, sometimes little helium as well. The final flash, therefore, contains a record of the star's earlier life. The death seen in one moment has been prepared by millions of years of burning, mass loss, and hidden interior change. The explosion also scatters the star's chemical inheritance. The outer layers hold elements built before the collapse, while the blast adds new products and throws them outward into the interstellar medium. Oxygen, silicon, sulfur, calcium, iron, and many other elements can be carried away in the expanding debris. Some of the heaviest elements require special conditions, and not all are made mainly in ordinary supernovae. Neutron star mergers are now known to be major sources of many rare heavy elements, and some unusual supernova environments may contribute as well. The calm truth is that the periodic table is not born in one place. It is assembled across many kinds of cosmic events. But core collapse supernovae are among the great distributors. They open massive stars and return their interiors to space. They send enriched gas outward, seed surrounding clouds, and leave behind expanding remnants that can glow for thousands of years. The Crab Nebula is one famous example, the debris of a stellar explosion observed on Earth in the 11th century. At its center is a pulsar, a rotating neutron star, marking the compact remnant left by the collapse. Around it, filaments of gas continue to expand, carrying the visible memory of the explosion. A supernova remnant is not only an afterimage, it is an active structure. The ejecta plow into surrounding gas, driving shock waves that heat the interstellar medium. These shocks can accelerate charged particles to high energies, creating cosmic rays. They can compress nearby material and enrich clouds that may one day form new stars. Dust can also form in the cooling debris, though some of it may later be destroyed by shocks. The remnant grows, thins, and changes shape as it meets the uneven medium around it. Long after the peak light fades, the supernova continues to reshape its neighborhood. The death of one massive star becomes part of the weather of a galaxy. It is violent, but it is not only destructive, it is a way the galaxy mixes itself, moving heat, motion, and heavy elements from the hidden core of a star into the spaces between stars. The compact object left behind depends on what remains after the explosion, and any fallback of material. If the core settles into a stable neutron star, the supernova has produced an object where matter is packed close to nuclear density. If too much mass remains, collapse can continue into a black hole. Sometimes material that was initially thrown outward may fall back, increasing the remnant's mass and altering the final outcome. The visible blast is only one part of the event. Beneath it lies the birth of an extreme remnant, and around it lies the spreading chemical shell. The supernova moment joins both directions, inward to compact matter and outward to galactic enrichment. It is the star's most dramatic release, and its most complete division. The core becomes something radically dense, while the envelope becomes a cloud expanding into darkness. To distant observers, the supernova may seem sudden, a new star appearing where no bright point had been seen before. In reality, it is not a new star but the final display of an old one. The light has spent ages in preparation, hydrogen fusion, helium burning, shell formation, ion accumulation, collapse, shock revival, radioactive decay, and expanding gas all contribute to the event. Its brilliance is brief because the structure that made it cannot last. The debris expands, the density falls, the glow weakens, and the remnant begins its long fading into the interstellar medium. Yet the matter released does not lose its importance. It carries the products of the star's life into future possibility. A calcium atom made or scattered in such an event may later drift into a molecular cloud. An oxygen atom may become part of a new star-forming region. Iron from ancient stellar deaths may enter planets, rocks, oceans, and living bodies, depending on where gravity later gathers it. The supernova does not decide those futures. It only opens the star and lets the material go. This is why the supernova moment is both an ending and a beginning without becoming a simple cycle. It is catastrophic for the star. The old balance is destroyed. The body of the star is broken apart. But the galaxy receives motion, energy, and elements that were locked away. The flash that briefly outshines surrounding starlight is followed by a slower gift, the spreading of matter into places where new structures may eventually form. In the deep calm after the blast, the remnant expands, the compact core spins or darkens, and the enriched debris thins into space. A massive star dies in a moment of extraordinary brightness, but that brightness is only the opening signal of a much longer transformation. The supernova is the soundless crossing from stellar life to cosmic inheritance, where collapse becomes light, and the star's hidden interior is finally returned to the galaxy. A neutron star is born in the innermost violence of a supernova, but after the flash has passed into space, the remnant itself remains almost impossibly quiet in its density. It is the collapsed heart of a massive star, the part that does not escape when the outer layers are driven outward. Before collapse, this core is made of iron group nuclei, crowded electrons, radiation, and heat. During the fall, electrons are squeezed into protons, producing neutrons and neutrinos. Matter that once follows the familiar architecture of atoms is forced into a state closer to the density inside atomic nuclei. The result is a sphere only about the size of a city, yet carrying more mass than the Sun. It is not a giant star anymore. It is not a white dwarf, held up by electron pressure. It is a deeper remnant, one in which gravity has pushed past the ordinary forms of matter and stops only when neutrons and the strong nuclear force resist further compression. A neutron star is therefore a boundary between the known and the extreme, a place where the rules of small particles become the structure of an astronomical object. Its birth begins as the iron core falls inward. The center reaches nuclear density, and the material stiffens. The inner core rebounds, helping launch the shock that may become the supernova, while the outer core continues to crash down and settle onto the newborn remnant. Neutrinos pour outward from the hot compact object, carrying away enormous energy. Most pass through the surrounding star and into space, but some help revive the shock and contribute to the explosion. What remains inside is not cold or settled at first. It is a proto-neutron star, hot, opaque to many neutrinos, and still changing as it cools and contracts. In its first moments, it is surrounded by falling matter, turbulence, and the after effects of collapse. It may gain additional mass before the explosion fully clears the surroundings. If it remains below the limit that neutron pressure and nuclear forces can support, it survives as a neutron star. If it gains too much mass, the collapse continues into a black hole. The difference depends on the original star, the explosion energy, the core structure, and how much material falls back. The surviving neutron star is supported by matter in a state far beyond ordinary solids, liquids, or gases. Near the surface, a thin atmosphere may exist, pressed flat by gravity. Beneath it lies a crust of nuclei and electrons arranged under immense pressure. Deeper still, nuclei become so crowded and neutron-rich that neutrons begin to drip out, forming an inner crust where nuclear clusters may take unusual shapes. Farther inward, the star is thought to contain mostly neutrons, with some protons, electrons, and other particles mixed in. The deepest core remains one of the great open questions. It may contain exotic states of matter that cannot be sustained anywhere else in nature for long. The behavior of such dense matter is described by the equation of state, a relation between pressure and density. Astronomers and physicists study neutron stars because each one is a natural experiment in this hidden physics. Its mass, radius, cooling, rotation, and gravitational waves can hint at what matter becomes when it is squeezed almost to the edge of collapse. The gravity at the surface is severe. A mountain on a neutron star could be only a tiny rise by earthly standards and still hold enormous weight. Any loose material is pulled down with incredible force. The escape speed can approach a large fraction of the speed of light. Light leaving the surface is stretched by gravity, losing energy as it climbs away. Time itself runs more slowly near the star than it does far from it. According to general relativity, these effects are not decorative details. They are part of what the remnant is. A neutron star is not merely dense matter in space. It is dense matter wrapped in strong gravity, where space-time is curved by a compact mass only a few miles across. Its presence can be felt in orbits, radiation, and the behavior of material falling onto it from a companion star. Many neutron stars are also born spinning rapidly. The collapsing core conserves angular momentum, so as its size shrinks, its rotation speeds up, much as a spinning skater turns faster when drawing in the arms. A massive stellar core compressed to city size can rotate many times each second. The neutron star may also inherit and amplify magnetic fields from the original star. In some cases, these fields become extraordinarily strong, producing magnetas, neutron stars whose magnetic energy can power intense bursts of high-energy radiation. More commonly, a rotating magnetized neutron star can appear as a pulsar. Beams of radiation emerge from regions near its magnetic poles, and as the star spins, those beams sweep through space. If one crosses Earth, telescopes detect regular pulses, like a cosmic lighthouse. The pulses do not mean the star itself is turning on and off. They reveal rotation, geometry, and magnetic fields. The regularity can be so precise that pulsars serve as cosmic clocks, though even they can change through sudden spin adjustments called glitches, likely linked to the star's interior and crust. The discovery of pulsars revealed that neutron stars are not only theoretical remnants, they are real bodies scattered through the galaxy, often moving quickly after birth. A supernova explosion may not be perfectly symmetric, and the newborn neutron star can receive a kick that sends it travelling through space at high speed. Behind it may lie an expanding remnant of gas, and at its centre, the pulsar may inject streams of energetic particles, forming a pulsar wind nebula. The Crab Nebula is one such system, where the rotating neutron star powers a bright cloud within the debris of an old explosion. In this way, a neutron star can continue to shape its surroundings long after the supernova's peak light fades. Its energy is drawn not from fusion, but from rotation, magnetic fields, cooling, and, in binary systems, from accretion. When gas from a companion falls toward a neutron star, it can heat to extreme temperatures and shine in high-energy radiation, and accreting matter can spin the remnant faster. Such afterlives show that stellar death does not always end activity. The density of a neutron star also gives it a special role in the origin of heavy elements. When two neutron stars orbit one another, they radiate gravitational waves, tiny ripples in space-time that carry energy away. Over long time, the orbit shrinks, and the stars can merge. In such a collision, neutron-rich matter can be thrown outward, building many rare heavy elements and producing light known as a kilonova. This is not the ordinary birth of a single neutron star, but it shows how these remnants remain part of cosmic chemistry. Yet a solitary neutron star mostly cools and slows, its surface temperature falls, its rotation loses energy, its beams weaken or move out of alignment. It becomes harder to detect unless it accretes matter or remains unusually hot or magnetically active. The object itself persists, a compact remnant made from the core of a dead massive star. It is not a black hole, because pressure and nuclear forces still hold matter in a finite body. It has a surface, however extreme. It has a radius, a crust, and perhaps layers that can crack, flow, or shift. It is still within the universe of matter, though at the far edge of what matter can bear. The birth of a neutron star is therefore one of the most dramatic transformations in nature. A stellar core made of atoms collapses until atoms lose their separate meaning. Electrons and protons become neutrons. A city-sized sphere inherits the mass of a star. Rotation becomes rapid. Magnetic fields intensify. Gravity bends light and time near the surface. The outer star explodes outward, while the inner star condenses into an object that can pulse for millions of years. It is a remnant, but not a simple ruin. It is a new kind of body, formed by death, governed by extreme pressure, and filled with questions about matter itself. In the sequence of stellar endings, the neutron star stands between the white dwarf and the black hole. The white dwarf is held by electrons. The neutron star is held by neutrons and nuclear forces. Beyond it lies the threshold where even that support fails. For a time, in this narrow and extraordinary state, gravity has not fully won. It has compressed the star almost to the final boundary, but matter still answers. The answer is dense, dark, magnetic, and precise, a small remnant carrying the memory of a massive star's collapse in every pulse it sends through space. A black hole begins not as empty darkness, but as a failed rescue inside a collapsing stellar core. In the death of a massive star, gravity first crushes matter toward a neutron star, forcing electrons and protons together until neutrons dominate the remnant. For many cores, This is where collapse stops. Neutron pressure and nuclear forces become strong enough to hold a compact body with a surface, a radius, and finite gravity. Yet there is a deeper threshold. If the remaining core carries too much mass, even neutron matter cannot support it. The pressure that holds a neutron star is not unlimited. It can resist gravity only up to a certain point. When the mass is too great, the remnant cannot settle. It keeps falling inward. The surface that might have become a neutron star is drawn down. The star crosses from extreme matter into a region where gravity determines the shape of escape itself. The result is a stellar black hole, a compact remnant surrounded by an event horizon, the boundary beyond which no signal can travel outward to the rest of the universe. The event horizon is not a material surface like the crust of a neutron star. It is a boundary in space-time. Outside it, light can still escape if it is aimed along an outward path. At the horizon, the escape speed reaches the speed of light. Inside it, all future paths lead inward. This does not mean the black hole pulls everything from far away without limit. At a distance, its gravity acts like the gravity of any other object with the same mass. The strangeness begins close to the horizon, where mass is packed into such a small region that space-time curves severely. Light bends. Time slows relative to distant observers. Matter falling inward heats, stretches, and loses ordinary routes back to space. The black hole is therefore not defined by darkness alone. It is defined by geometry, by the way gravity reshapes the possible directions of the future in the final collapse. The difference between a neutron star and a black hole may be decided by material that fails to escape. A supernova can drive outer layers outward, but some matter may fall back onto the compact remnant. If a newborn neutron star gains too much mass, it can collapse further. In other cases, the core may be so massive that a black hole forms promptly, perhaps with a weaker visible explosion or with much of the star falling inward. The pathways are varied, and massive star death remains an active field of study. Rotation, magnetic fields, binary companions, and mass loss through stellar winds all influence the final outcome. A star that begins very massive may shed much of its envelope before collapse. Another may be stripped by a companion. The black hole threshold is therefore not marked by a simple original birth mass alone. It is marked by what the core becomes at the end, how much mass remains bound, and whether any pressure can still answer gravity. When the answer is no, the collapse passes beyond the neutron star state. Classical general relativity describes the inward fall as ending in a singularity, a place where density and curvature become infinite. This prediction shows how extreme the problem becomes, but it also points toward incomplete knowledge. Infinite density is likely not a complete physical description of nature. It marks the place where known theories, especially general relativity and quantum physics, are not yet fully joined. What can be said with confidence is that the event horizon forms, and once formed, it hides the innermost region from outside view. No light from within can reach a telescope. No signal can report what matter experiences after crossing inward. The black hole is visible only through its effects on what remains outside. This hidden quality gives black holes their calm but unsettling power. They are not holes in space in the ordinary sense. They are regions where gravity has become so strong that space-time closes off outward paths. A black hole can be detected when it pulls gas from a companion star. The gas does not usually fall straight in. It forms a swirling accretion disk, heating through friction and compression until it shines in high-energy radiation. Near some black holes, magnetic fields and rotating plasma can help launch jets that stream away from the region around the hole. Though not from inside the event horizon itself, A black hole can also be found through the motion of stars orbiting an unseen mass, or through gravitational waves released when two black holes spiral together and merge. In this way, black holes become known not by direct sight, but by the behavior of matter, light, and space-time around them. The stellar black hole is one member of a larger family. Supermassive black holes sit in the centers of many galaxies, but the black holes born from dying massive stars are more intimate in scale. They are the final answer for cores too heavy to become white dwarfs or neutron stars. Their mass may be only several times that of the Sun, or larger if the collapsing star has retained enough material. Their size, measured by the horizon, is small compared with ordinary stars. A black hole with a mass of several suns may have a horizon spanning only a few tens of miles. Yet within that compact boundary lies the consequence of an entire stellar core losing every form of support. The event horizon also changes the meaning of an ending. A white dwarf cools, a neutron star can pulse, flare, or accrete. A black hole has no visible surface to cool and no material crust to crack. It is described from outside by properties such as mass, spin, and electric charge, though astrophysical black holes are expected to carry little net charge. Spin can be important because collapsing stars often rotate, and a rotating black hole drags space-time around it. This frame dragging influences accretion disks and the behavior of matter near the horizon. The remnant can continue to grow by swallowing gas, dust, stars, or other compact objects, but anything that crosses the horizon is no longer part of the observable universe in the usual sense. Its mass and energy still affect the black hole's gravity, yet its detailed form is hidden. This makes the black hole both simple and mysterious. From far away, it can be described with very few properties. Near the horizon, it represents one of the deepest limits of known physics. The birth of a stellar black hole may or may not be accompanied by a bright supernova visible across a galaxy. Some massive stars may collapse with a strong explosion, leaving a black hole after fallback. Others may collapse more quietly, with much of the star disappearing into the remnant and only a faint outward signal. Astronomers search for such failed supernova by watching massive stars that seem to vanish or fade without the expected blast. These possibilities remind that black hole formation is not always a single dramatic scene. Sometimes the universe may mark the creation of a black hole with fire. Sometimes it may do so with absence. In either case, the threshold is crossed when gravity overwhelms every available support, and the core becomes hidden behind a horizon. This does not make the material history of the star meaningless. Before collapse, the star may have created elements in its shells and lost some through winds. If an explosion occurs, enriched matter may still be scattered into space. If collapse is more complete, more material may be swallowed, and less may return to the galaxy. The black hole ending can therefore be less generous than a supernova that leaves a neutron star, depending on how much of the star escapes. Yet even black holes participate in cosmic change. Their mergers release gravitational waves, their accretion disks can shine with extraordinary power, their presence can shape binary systems, star clusters, and galactic centers. They are dark only in the narrow sense that light cannot come out from within the horizon. Around them, the universe can be intensely active. The black hole threshold is the last boundary in the ordinary sequence of stellar death. Below it, matter finds ways to resist electrons in a white dwarf, neutrons in a neutron star. Beyond it, no known pressure can halt the inward fall once enough mass is confined. The dying star ceases to leave behind a surface and instead leaves a border. The border is silent, smooth, and absolute. It does not glow on its own. It does not reveal what lies inside. It only marks the place where escape ends. In that hidden boundary, the life of a massive star reaches its most severe conclusion. Gravity, which first gathered the star from a cloud, finally closes around the core completely. The furnace is gone, the matter is concealed, and the remnant becomes a dark geometry written into space. The deaths of stars do not end with the objects they leave behind. A white dwarf cools in quiet density, a neutron star pulses or fades, and a black hole hides its center behind an event horizon. Yet the larger consequence moves outward through the galaxy. Every star begins from interstellar matter, and every star changes some portion of that matter before returning it or locking it away. The universe into which the first stars were born is not the same universe that later forms rocky planets, icy moons, metal cores, and carbon grains. The earliest material is mostly hydrogen and helium, with only tiny traces of other light elements. It is simple, poor in the ingredients that make solid worlds. Stars alter that simplicity. In their cores, they fuse light nuclei into heavier ones. In their winds, giant phases, nebulae, explosions, and mergers, they release part of that work back into space. Stellar death is therefore one of the great engines of cosmic enrichment. It is how the private chemistry of a star becomes public matter for the galaxy. A lower mass star contributes gently. After spending billions of years turning hydrogen into helium, and later helium into carbon and oxygen, it expands into a giant and loosens its outer layers. Those layers drift away as winds and glowing nebulae, carrying material that has been processed, mixed, and enriched. The exposed core becomes a white dwarf, holding much of the carbon and oxygen ash in a compact remnant, while the released gas spreads outward. Over time, the planetary nebula fades, but the atoms remain. They enter the interstellar medium, where they may mix with older gas, dust, and debris. A massive star contributes more violently. It lives quickly, builds layered shells of elements, and collapses when iron ends the sequence of useful fusion. Its supernova can throw oxygen, silicon, sulfur, calcium, iron, and other products into space, stirring the surrounding medium with heat and motion. If it leaves a neutron star, the remnant may later merge with another compact object, helping create some of the rarest heavy elements. If it leaves a black hole, part of the star may vanish from ordinary view, yet winds, earlier mass loss, or explosive ejecta may still have returned enriched material. No single kind of death makes the universe complete. The periodic table is assembled across many settings, each with its own conditions. Low and intermediate mass stars enrich quietly. Massive stars enrich by winds and explosions. Neutron star mergers provide neutron-rich environments for many heavy nuclei. White dwarf explosions in binary systems can create large amounts of iron group material. The chemical world is a collaboration of endings. Gas ejected by one star does not immediately become a planet or a living cell. It spreads, cools, collides, and mixes. Shock waves from supernovae can compress some regions while heating others. Stellar winds carve cavities and pile material into shells. Dust grains form in cooling outflows and explosive debris, then drift through radiation, magnetic fields, and turbulence. Molecules gather in cold, shielded clouds where dust helps block destructive light. Gravity works again, as it did at the beginning of every star. A portion of enriched gas becomes dense enough to collapse. Within the collapsing cloud, new stars form, now carrying traces of earlier generations. Around some newborn stars, disks of gas and dust flatten into rotating planes. Inside those disks, tiny grains collide and stick. Ice gathers where temperatures are low enough. Metals and silicates collect nearer the warmer regions. over long spans. Dust becomes pebbles, pebbles become larger bodies, and some larger bodies become planets, moons, asteroids, and comets. The elements that stars made or released become the material from which worlds take shape. This is the quiet connection between stellar death and planetary birth. A rocky planet requires silicon, oxygen, magnesium, iron, nickel, sulfur, aluminum, calcium, and many other elements that were not available in abundance at the beginning of the universe. Atmospheres require volatile elements and compounds. Oceans require oxygen and hydrogen, with salts and minerals shaped by heavier atoms. Organic chemistry depends especially on carbon, along with hydrogen, nitrogen, oxygen, phosphorus, sulfur, and trace metals. These elements are not all made in the same star or the same event, but they are all part of the long enrichment of galaxies. The ground beneath a future world is therefore not separate from ancient stellar interiors. It is the settled consequence of many furnaces, winds, and explosions. Even the iron in a planetary core may have passed through more than one cosmic stage before becoming part of a world. An atom can be made in one star, released into space, mixed into a cloud, joined to a dust grain, incorporated into a planetesimal, melted inside a young planet, and finally buried in a core or lifted into a crust. The universe remade by stellar death is not only richer in chemistry, it is richer in structure. Heavy elements allow gas to cool more effectively because atoms and molecules can radiate energy away. Cooler gas can collapse into smaller fragments, helping shape later generations of stars. Dust changes how light moves through clouds. Metals alter the atmospheres and interiors of stars, influencing their lifetimes and winds. Planet formation depends on solids, and solids depend on elements heavier than helium. The first stars may have been born in a simpler darkness, but later stars form in environments already written over by previous deaths. Each generation inherits a changed medium. This inheritance is uneven. Some regions of a galaxy become enriched quickly after massive stars explode. Other regions remain more primitive for longer. Astronomers read those histories through spectra, the fingerprints of elements in starlight and gas. A star's atmosphere can preserve the composition of the cloud from which it formed. Ancient stars with very few heavy elements reveal early stages of enrichment. Younger stars, including the Sun, contain more of the elements that earlier stars released. In this way, the deaths of stars become readable long after the stars themselves are gone. Their ashes are written into the light of later generations. The Sun and its planets form from such inherited material. The solar system is not made from untouched primordial gas alone. It contains elements forged across earlier stellar lives and deaths, gathered into a new cloud before the Sun was born. Meteorites preserve some of the earlier solid material of the solar system, including grains that formed around other stars before the Sun existed. These pre-solar grains are tiny messengers from previous stellar environments, showing that material can survive the journey from one generation into another. This does not make stellar death gentle in any immediate sense. A supernova destroys the star that produces it. A black hole hides matter forever from outside communication once it crosses the horizon. A neutron star is born from crushing collapse. A white dwarf is the exposed core of a star that has shed its body. These are endings, real and irreversible for the stars involved. Yet on the scale of the galaxy, endings become transfers. Matter is transferred from cores and envelopes into interstellar space. Chemical complexity is transferred from one generation to the next. The same gravity that once gathered a star later gathers some of what the star returned. There is no need for intention in this pattern. It is not a perfect circle, and not a promise that every atom finds a new world. It is a natural circulation shaped by collapse, fusion, loss, explosion, cooling, and collapse again. In that circulation, the death of stars becomes one of the reasons the universe can keep changing. Without stellar death, much of the heavy material would remain locked away. Without heavy material, rocky planets would be rare or absent. Without earlier generations, later generations would form from simpler ingredients. The sky would still contain light, but its possibilities would be poorer. White dwarfs, supernovae, neutron stars, and black holes are therefore more than final states. They are thresholds where stellar lives become galactic consequences. Some remnants hold matter in silence. Some scatter matter in fire. Some later collide and forge rare elements in gravitational waves and radioactive glow. Some vanish behind horizons while their surroundings blaze. Together, they show that a star's death is not only the fading of a light, but a rearrangement of what the light has made possible. Across the galaxy, enriched clouds drift in the dark, carrying atoms from many vanished stars. In time, gravity may fold them inward again. New stars may ignite. New disks may settle. New worlds may take shape from old stellar remains. The universe is remade not all at once, but through countless endings, each leaving behind a trace of pressure, heat, ash, and silence. In the long view, the death of a star is not the opposite of creation. It is one of creation's oldest methods, turning the spent cores of light into the raw material of everything that comes after.